E para fazer as perguntas, a gente vai continuar utilizando o sistema do Mentimeter. Então, vocês fazem um cadastro lá para fazer as perguntas para o nosso convidado de hoje, o professor Patrik. Só mais um lembrete antes da gente iniciar, se vocês quiserem ter acesso aos vídeos dos últimos seminários, vocês podem acessar o canal do YouTube da ABPOL, tá? Então, lá a gente está disponibilizando as gravações. Acho que é isso. Professor Patrik, in the name of the ABPOL Sul, I would like to thank you very much for accepting our invitation to present this webinar today. We appreciate. And now I invite the chairman of this session, Professor Sandro.
Okay. All right. Thank you. Thank you, André, for the introduction. And as a host here, it's my pleasure to introduce you, Professor Patrik Fernberg. Okay. So I'm gonna, before he starts his seminar, I'm gonna read a brief resume so that you can know what he's been doing recently. Okay, so Patrik Fernberg is since 2019 professor in polymer composite materials at Luleå, University of Technology. Prior, he worked for 17 years at RISE Seacomp, a Swedish research institute with focus on applied research on polymer composites and structures. During the last 4 years at the institute, Fernberg held the position as head of research. He has worked with different research and development projects since starting his PhD studies in 1997. Fernberg's technical expertise is within the area of high-performance composite materials, their constituents, manufacturing, and use in lightweight structures. The interest in composites research is generic. Recent years have, however, been largely devoted to aeronautical grade composites, in particular high-temperature polymer composites. Okay, so Professor Patrik, please, you can share your screen now. Thanks a lot for having accepted our invitation, and I will be saving here the questions that the audience makes, and I will ask you in the end, or if one appears that I would like to do straight away, I will ask you to, if I can, okay? So yes, please feel free. Thanks a lot again for having accepted our invitation, Patrik. Thank you.
Thank you. First of all, thank you to the organizers for inviting me to give this seminar. Thank you to Professor Sandro, particularly for the communication before and in the context of the seminar. So I will now try to start share my screen again and see if it works. I hope you can see the presentation. Okay, that's good. Yes, as Sandro told you, I'm Patrik Fernberg from the Luleå University of Technology in Sweden. So this is to start out, where is Luleå? And maybe Sweden is the northern part of Europe. Luleå is in the northern part of Sweden, meaning that we're entering a very cold and dark period at the moment, whereas you do go towards the opposite. But it's a good place to be in any case. We had the opportunity to have a exchange with Brazil and Professor Sandro over the last few years, which is very appreciated, and we have some colleagues here. I noticed that in the audience who are also working and have been working with us. So I promised to, or I agreed to give a little bit of talk on polymer composites for aero-engine applications, and that is reflects my recent work, and I will try to see if we can switch so it works. Well, the outline of my presentation is that I will try to first of all give a bit of a background in general about polymer composites in their how they're used in aircraft structures, in how they're used in aero engines. And with that as a background, I will discuss a bit more in detail about the work that we've been doing on, especially on temperature resistant polyimide based polymer composites, a bit of the materials, their manufacturings, highlight some properties and the challenges, and with that, after that, then just give a summary. So it will be first a background and then trying to dig in a bit more into a certain class of polyimides and composites that we've been working quite a lot with here, and we think is quite interesting. Starting with the background and in a very general picture, most of us who are working with composites are very well aware that the lightweight potential of composites is useful for the use in the aviation and aeronautics sector, and this sector is, at least until recently, until everything turned upside down with the pandemic, there was a prediction over the last very long period of time, there's been around 4% annual growth in this industry, sort of in the overall aeronautics industry, which is quite a big growth. This has seen, obviously, there will be a setback in due to the decrease of traveling during the COVID situation, but most likely and hopefully we'll expect that we come back to a new normal situation after some time, and that it's likely that although there could be a difference in growth rate, still that it's expected to grow further. The drivers have been sort of the globalization and economic growth of wealth in general for the population on the earth. But with that growth also comes environmental consequences that I think all of us are aware of. And if we look at the graph here, this is sort of estimates recently published by European not authorities but organizations, and it's sort of a common view from their aeronautics and industry that with a 4% growth on the y-axis we have gigaton of carbon dioxide emissions from aviation, and then the years on the x-axis. So with the predicted growth, if nothing happens, then the forecast is that the CO2 emissions from aeronautics will increase radically over the next years until 2050. To avoid or to come around this, if a lot of research is going on into the aeronautics or aircraft industry, and this traditionally over the last few years there's been a reduction of around 2% in fuel efficiency of aircraft over the last few years. So per year there is a efficiency improvement of 2%, and if that continues, we will expect to have follow the middle line here, which is indicated on in the middle of this image. But there's a large gap as compared to the two lower lines, which are really the targets of the aeronautics industry. The Air Transport Action Group, ATAG, has a goal of reducing the environmental impact by 50% by 2050, and even in Europe now there's an ambition to have a carbon neutrality for all sectors by 2050, meaning that, and the arrows then meaning here that there's a need to decrease or increase the fuel efficiency even further, meaning that radical technology development is also needed in the aviation industry. So the driver that the industry is seeing is now the environment, really, to reduce the environmental impact of the aviation industry. And if we look back on this 2% per year improvements that has been seen, we find composites as a part of the solution for in many cases because their lightweight potential and the recent aircrafts. If we look at Airbus A350, which is one of the more recent aircraft they issued or started to produce, as well as the Boeing 787 Dreamliners. The common denominator of these aircrafts are that they are, one common denominator is that they're largely made from composites. Almost more than 50% of the structure, including the fuselage, wing and empennage at the back of the aircraft structure is made from composites, and that is one cause for the, by reducing the weight, the fuel efficiency of these the aircrafts have increased. So where are we going at the moment? If we look at some of the innovative concepts that currently are on a research stage or concept stage, there are some ideas presented a few years ago, but also that are currently considered for next sort of concept for next generation aircraft. One is represented here by having the engines close to the fuselage and using the boundary layers where the airflow is good for reducing the need for thrust to drive the aircraft, so it creates a beneficial sort of what is called it. Beneficial sort of it doesn't require much force or thrust to drive the aircraft forward. Another way to reduce the drag is to have, as is indicated in the right, by having so-called high aspect ratio wings, long slender wings, again lightweight, to again reduce the drag of the aircraft. New architectures also, concepts include flying wings that combines aerodynamic efficiency and structural efficiency by integrating the structure already in the wing. So these are concepts, and as well as the recent years, the interest for electrical propulsion has increased, and there are different concepts that are suggested. Where in this case, distributed turbine generators and electric fans on the wing structures in order to get away from the use of fossil kerosene fuels and use electricity as power for fuel. In the last few months, or it was recently, I think it was in September, Airbus introduced also a concept and an ambition to develop new alternative fuels, meaning that hydrogen propulsion using hydrogen gas as fuel in the aircraft. And this is something that currently is being launched in Europe or by Airbus as a concept aircraft, a Series E concept aircraft, where they foresee that in the next possible solution to next generation could be, for instance, a turbofan aircraft with hybrid turbofan engines that provide the thrusts. And the fuel, in this case, the liquid hydrogen, is stored in the rear of the airplane. So basically, it's an extension of an aircraft. And instead of having fuel in the wings as a kerosene fuels in the wings, there's liquid hydrogen in the rear. Similar for a turboprop and more regional aircraft type, they foresee, but also envisage that there could be studies on blended wing body concept where the hydrogen storage could be introduced in the wing structure or under the wing structures. So these are very recently presented concepts and sort of indicates an increasing interest in hydrogen as an alternative fuel. And of course, this opens new research channels also for the composite community, which I will come into. Not only the body structure or the structure of the aircraft is made with composite. If we look in recent developments of aero-engines, we also find carbon composites in these structures. And sort of one of the drivers for using composites, we can find the reason in the trend of if we look at the turbofan engine as indicated here on the image, there is one sort of measurement called or parameter called the bypass ratio, which is the ratio of the mass flow outside the engine, sort of in the exterior part here. If we look on this engine, we see that a lot of the air that is passed through the engine is passed outside the actual compressor stage. And it has turned out that by increasing the bypass ratio is one way to improve the fuel efficiency of turbofan engines. And consequently, if we look over the development again over time, the trend has been, if we look at the transport engines in particular, and we have the bypass ratio on the y-axis, and again the period of time up till 2020, we see that the bypass ratio is constantly increasing to create more and more energy efficient engines. And with the increase in bypass ratio, that also implies that the diameter of the engine will increase. And with the diameter increase, the incentives for having lightweight materials also increase, meaning that that has led to a development of increased use of composites also in aero engines. So if we look then at where the composites are used in a turbofan engine, typically where we find polymer composites. If we can take this turbofan engine and we see the outer region outside the red lines here is really where the air is mainly bypassed. So it's the cold air that is bypassed here, meaning that the temperature requirements on the materials aren't really that extreme for these materials, for these structures, and polymer composite can be used, the traditional ones. If we go inside the red towards the compressor or at the front of the compressor stage, the temperatures are increasing and polymer composites are not, traditional polymer composites are not that useful, but this is an area where I will talk a bit later also. But we see that, for instance, the fan blades in the front of the engines, they are made in for some recent turbofan engines, they are made in composites, carbon fiber reinforced epoxy. And research also is done on the outlet guide vanes, OGVs, that are placed behind the fan, and really these are vanes that are static, that are not rotating in the engine, but they really holds the entire transfer the load from the compressor to the outer fairing of the engine and then on to the aircraft. So it's a highly loaded structure, And currently, there's been quite a lot of research in using carbon composites also for that use. So again, the carbon fiber fan blades you find in the General Electric engines, and this is a rather large engine. So hence the person here on the right is small compared to, or in the similar size as a fan blade, rather large structures. The LEAP, another example is a LEAP engine, which is the engine blades are produced by a French company, Safran, who are also making them in carbon composites. And this engine is used in a lot of the Airbus A320 and Boeing 737 MAX aircrafts. So they're already in use. As indicated, the outlet guide vanes, to my knowledge, they're not used in any Aero-engine at the moment, but there's quite a lot of research going on, and this is a picture of a demonstrator structure that was built in a European project some years ago. And to the right, there is some. I mainly took this image because the two of my former colleagues are on that image, so they can be found there. So with this as a background, I think the motive here to give that background is to convince and sort of argue that aeronautics technology development will continue to be a strong driver for advanced composite research. And in my opinion, what is currently the main areas for the research that is going on and will be required for the future is one of the things that is highly needed with increasing use of composites is this cost and eco-efficiency driven manufacturing. A lot of the structures are made with previously with autoclave curing and then that for the fuselage and the wing structure. This is a very costly method. So out of autoclave processing of thermosetting is something there's a continuous need to develop these technologies and mature them. Also, bio-based composite constituents, both fibers and matrices is also areas that need to be developed, as well as thermoplastic composite processing and fiber reinforced thermoplastic composites for fuselage. And there's quite a lot of work going on in developing peak and type of this high performance polymer composites, as well as recycling, which is a very, very important aspect of all composite contexts and when trying to develop technologies for a more environmental friendly and recyclable future. Another challenge are these large and integrated composite structures that, for instance, the large and slender wing bodies that need to be manufactured. They are challenging because shape control of these and residual stress development because of the thermal mismatch between fiber and matrix is important. Joining continues to be an issue. And again, yes, tailor and optimize impossible structure, non-destructive inspection and repair, clearly an area. If we look at the trend now to start to look into more to hydrogen as an alternative fuel will require new storage solutions for the aircraft. And most likely the composite pressure vessels are likely to be used in my opinion in this hydrogen as hydrogen storage if in these new structures. So it will put another and of course the safety aspects will be important. So materials manufacturing the size of composite pressure vessels or storage solutions for hydrogen will be an important aspect that need to be developed. Multifunctional composites like morphing structural batteries is an area which is also interesting, where you can use composites both for storing energy and as a structural component and thermal management. But the last area, which will lead me then to the next stage of the presentation, is really in order to be able to also to produce these larger engines and to have temperature resistant composites is an area that at least in my opinion that is an interesting and needed possible area to do research, which can be used in also in aero-engines. An aspect there is really manufacturing, because it's not very easy to manufacture. The influence of these extreme environments, the mechanical and temperature loads that they will experience, and fatigue or degradation over time, and fire are aspects that is something that is of interest for these composites. So this leads me to the second part of the presentation, where we will look more closely into the composite materials for the high temperature application. I will, on this very indicative chart on different polymer, where the glass transition temperature is on the y-axis, and in this case it's cost on the x-axis, indicates some of the high performance polymers that can be used for potentially for high temperature applications. But I've shaded out the ones that are really below, let's say TGs below 200 degrees, which means phenolics and epoxies are not will not be discussed in that much in the coming slides. So what we consider or what I consider then when looking into high temperature is the bismallamides, cyanide esters, polyimides, and phthalonitrile. All of them are more or less expensive. Well, all of them are expensive, but some are extremely expensive. But all of them have high glass transition temperature and various degrees of thermal stability. I will present the polymers that we've been working mainly is the polyimides that we will I will present a bit on in the coming slides, and what we've done in the area of polyimide composites development. Both in my previous work and what I continue to do also at the university. So this is the development strategy of when we work with the high temperature polyimides. It's not nothing revolutionary here for composite peoples. We are all aware that in order to achieve performance of a structure made in composites, we need to take into account the manufacturing, the material and the properties and the design in a very holistic way, since we manufacture the structure at the same time as we do the material, and we also we design both the meso micro structure also in the same time, and this will influence the manufacturing and the type of material we can use. So this is not a surprise to you. What we did was we started it really in 2012. So it's been going on for it's about 7-8 years now, and we've been using mainly polyimide types. We've been working with end users and material suppliers, universities and research institutes, the ones that we have, and try to mature technology for polyimide, the high temperature polyimides in simultaneously in different areas, both when it comes to materials, manufacturing, and properties, and gradually increase the complexity of the components. Early on in the development, we started out with postulating or agreeing that we should we have been mainly focusing on the process of resin transfer molding, where we use for manufacturing, meaning that we have worked mainly with systems or where we start with a dry preform to manufacture a preform, to lay up and drape the preform in a preform tool, and then put the preform, the dry preform, in a mold, and close the mold and inject the resin, the liquid resin into the mold, and then cure it in a mold, demold, and do the final processing. So this is the same process that is used, for instance, for some of the blades, and also for some other applications. So this is the process we've been mainly looking into, and then we've also been using. Typically, we've been using a lot of this, as you will see. The processing of the high temperature material is done at high temperature, meaning that we need to adopt the reinforcement to that. So we can't really use so-called, not so much of non-crimp fabrics with stitches, or we use primarily weaves, carbon fiber weaves, and the baseline material we've been using is a 8-harness satin weave most of the time for the development work that been, but also in some cases used other alternative architectures, like plain weaves, thin ply materials that is lower surface weight reinforcement that can produce really thin ply composites. These are a bit coarser when it comes to the structure. We've been working closely together with a company that develops and produces polyimides, this chemistry. So we developed this together with them. This Phenylethynyl-terminated polyimide system, also sometimes referred as a PETI. This is a thermosetting resin. When it's provided, it comes as a low molecular weight resin formulation, and you see the picture of how it looks like when it is delivered to for processing. It comes like a solid material or a powder in its uncure state. It's based on the SX6-FDA deanhydride base, and then on that is in an imidization process, that's creation of a reactive, or reacted on this end capper, phenylethynyl and end capper onto the structure, and also to some extent some reactive spacers that are also chemically reacted onto this to create the polyimide monomer that then can be, in the process that we're doing, we're cross-linking this to create a polyimide, highly cross-linked polyimide with high TG. This is due to the low molecular weight of the monomer or the oligomer. This is feasible for processing with RTM, and we can achieve up to 370 degrees glass transition temperature with the standard cure that we're doing. So what we've been doing in the early stages of development, when looking into the first step to see how to work with these materials, have been to look into simple or straightforward DSC analysis to run dynamic heating experiments with the primary goal to analyze the cure kinetics and the onset of curing reactions. So this type of DSC curves shows here that the onset of curing that is indicated by the onset of the peak or the peak that is upside down the valley here indicates when we start to have a reaction in the cross-linking, and there's an onset of this curing that starts at around 300. In this case, it indicates 360, but really the curing is starting a bit earlier than that, so we can have reactions that are started at lower temperature than that, but the main reaction takes place at 360 or even higher than that. The total heat of reaction during a cure is around 210, 220 joules per gram. So it's slightly lower than a typical epoxy system in terms of reactivity and exothermic reaction. Rheology characterization is an important thing to characterize when looking into the processability of these type of resin. And for that purpose, we've been using rheometer to both in viscometry mode, where there's a continuous rotation of the two, continuous shearing of the viscous fluid, and an oscillation mode, and where we detect the complex modulus and complex viscosity and sort of both the elastic and viscous part of the response. So two modes. The first one, the complex viscosity, we've been using primarily to estimate the time to gelation of a curing system in order to understand how long time do we have for processing these materials. So these are complex viscosity measurement made at 330 degrees. So it's not where we have the highest reaction rate, but we notice that in these cases we determine this is for elastic and viscous modulus, and the filled circles are for the elastic part, and the viscous part is the open circles. And typically, traditionally, what one says is the time to gelation, and is determined in experiment in this rheology type of setup when the intersection between the elastic and the viscous part, so when they cross each other, is an indication of the gelation. And in this case, we can see that at 330, we don't have much time, but we have around 15, 20 minutes in order to fill the mold, which is quite a short time, but still something to work with. Also, when filling something in an RTM process, it's important to have a good, sufficiently low viscosity, and that is also then a challenge for these kinds of systems, because we are, as you see here, the shear viscosity profile, which we also used rheometer to determine. This one starts viscosity on y-axis and temperature on x-axis, and temperature-wise, it starts really at 220 degrees. So we have, as you remember, there was a solid material to start with, but as we increase the temperature, eventually at around 200, 220, we melt the monomer, and then it starts to behave like a liquid. So by increasing the temperature, we reduce the viscosity significantly, and the increase that comes when we go toward high temperature is because this is then a sign that we start to have some curing reactions, or at that stage, meaning that there is some cross-linking going on. And when we developed the material, we were having targeted that, saying that we want to have a process window that allows us to have a viscosity that is below 600 millipascals seconds. And our measurements indicate that we have below 600. This is the inner graph is just a higher magnification of the curves, showing that we have below 600 millipascal between around 260 to 320 degrees. We have a process window which we can use for mold filling. So with that information, one can start to do composite manufacturing, and for that purpose we have used an RTM facilities for high temperature RTM. This unit has a possibility to process resin with temperatures up to 300 degrees. And essentially on the image, let me see. To the right here, you see this is underneath some insulation here. There is a barrel, a cylinder that inside there's, which is heated, and it contains also a piston that then can use to push the resin into the cavity. From this chamber, there is this heated pipe that goes to the RTM tool that is located in a tool, mold tool carrier here, and it's electrically heated. This can give heat up to 300 degrees. So what we do in practice or what is done in practice as a curing procedure is that for these materials we start by melting and homogenizing the resin inside the chamber and keep it at 240 degrees because we know that it melts there. We do a degassing operation at 240 degrees. It is liquid, but it's rather high viscosity, but there's no reaction. And we are able then to inject the resin with that temperature through the pipes in this region, and then do isothermal cure inside the mold, keep the mold at 320 degrees in order to reduce the viscosity and do the mold filling. And then do an isothermal cure, heat the tool, do that isothermal cure for 60 minutes at 12 bar, so it's high pressure, isothermal cure at 370 degrees, and then cooling slowly down to room temperature for demolding. So these are all the laminates that we have manufactured. We are typically flat laminates. There are also with a typical cross section here that is, you can see. Well, I start to have some issues with my presentation here. Let me see if I get back. I apologize. Run DMTA characterization to characterize the thermal properties, and we see that we have some materials that are behaving like we're expecting with a TG of around, in this case, no post curing. There is an onset TG of around 350. We do also have looked into the influence of post-curing on these materials. In this case, we have done tests where we both characterize the sample weight before and after post-curing it for 400 for 2 hours at 400, 420, and 440 degrees, and then measure the sample weight, and again characterize the number of defects you have in the format of cracks on the materials. And this is a bit peculiar, but we notice here that with increasing post-cure temperature, we have post-cure temperature here and TG on the y-axis. There is a tendency that post-cure, what we measure is that post-cure temperature decrease continuously with the TG increase continuously with post-curing temperature. And if we look at the nitrogen, when we cure it in nitrogen, we have a higher glass transition temperature than when we do it in pure air. What is peculiar is that we don't measure an upper limit in the tests that we have been running. We don't have a very good explanation to this yet or at the moment, but it's not likely that we have it need some kind of artifact. We're thinking that this is. Looking at the weight loss after post-cure, we notice that the weight loss after immediately we have the after post-cure with blue and after DMTA with red ones here, with red bars. We notice that the weight loss after post-cure is between 0.5 and 1.5%. The first, we know that just from drying the material, we usually lose around 0.4%, 0.5%. So to a large extent, this weight loss is because we're drying the materials. Then there's a weak tendency that weight loss increase with the post-curing temperature, but not significant. After DMTA, definitely there is a decrease, but that is rather expected since we're going up to very high temperature and we're doing it in air. It was a bit difficult to conclude much, but because of the variation in initial properties of the material. When we look at this material, we notice that that there is on the surfaces that there are micro cracks that are developing, sort of cracks in the material that are developing due to the aging, and we see that the increase in numbers is around 10 to 40% on the surface of these materials on the edges, and there are more cracks in the outer layers, which is clearly something that need to be taken into account when looking into how they operate on the surface. So when looking at the mechanical properties, we also have done that, of course. We done tests at different environments. So the green bars here are measurements for tension, and the left graph is stiffness versus different for different cases, and the right graph is strength. And the green bars is always tension. We notice that the leftmost ones here, the pair of are at room temperature. These are the properties we measure at room temperature. If we increase the temperature to 320 degrees and test the properties at that temperature, there is a decrease mainly in compressive properties in terms of stiffness. And if we then go further to the right in the stiffness graph, we find again, specimens that are tested at our room temperature, but then are aged, in this case, in one case for 500 hours, and in the other case for 1,000 hours at 320 degrees. So when we compare it to the first graph, we notice that, of course, there is a decrease also because of the aging, and the properties decrease more in compression. Compressive properties decrease more than the tensile properties. And the difference is very much magnified if we look at the strength properties to the right. For the difference between tensile properties, again, are not, at least between room temperature and 320 degrees test, are not very much affected, but the strength properties are clearly decreased quite a lot, and when it's aged at these very aggressive temperatures. So coming to where do we need to work, continue to work in order to take this into a bit more elevated state of knowledge and more maturity, reach more maturity. The 3 areas I would like to raise here is cure optimization and residual stresses. This is critical for these kind of materials, and we need to continue to work to understand better the cure kinetics and property development during cure. One way to do this is to understand viscoelastic contribution to stress relaxation that actually occurs during manufacturing at this temperature. The other thing is thermal oxidative stability. Again, the influence of physical and chemical aging. So work to identify and decouple the degradation mechanism that occur at high temperature. And something that I haven't mentioned a lot is the fire resistance. But I will. So cure optimization and residual stresses. What is this? Just to illustrate why this is so important, especially for these composite. If we consider the different layers, when we do the cure and everything is in a liquid state, then it's a stress-free state. And if we think of this as a laminate, viewing the edge of a laminate, we know and have the fibers in the outer layers are in the 0 degree direction, and the in the middle layer coming out of in the 90 degree direction. There's a big difference in thermal expansion coefficient for these different layers. So what happens when we cool it to room temperature? If we just consider the free plies, the outer plies, which are the 0 degree direction, they don't want to shrink at all because it's carbon fibers with very low thermal expansion coefficient, whereas the middle layer wants to shrink. But because they are glued together, they can't shrink, or they will shrink just the same amount. So, and this means that the 90 degree layers will be subjected to a tensile stress because it wants to shrink, but it can't shrink. And whereas the 0 degree layers are on compressive loading. So especially the tensile loading on the 90 degree layers is very important and provides very high stresses and this is what creates sometimes a crack that we observe. So if we just take the linear elastic laminate theory, we know that the residual stresses depend on the thermal expansion coefficients, the stiffness, and the delta T. And in this case, the delta T is up towards 300K, so it's very large. And this is really if we just calculate a simple estimate, we notice that in principle, the stresses that are generated in our cure is up towards 75 megapascal, which is almost, well, in the range of the theoretical strength of a 90-degree layer in the 90-degree, in the transverse direction. So it is more surprising that it doesn't crack more. So this is something that we're trying to develop an understanding further on, because it's very important both for the part shape deformation and all the built-in residual stresses in the material. It's also very important and to also take into account the interactions with a tool, since we're working with RTM properties processing. And if there are other stress dissipating mechanisms. I think I will skip this one. Another area is a thermal oxidative stability, the influence of physical and chemical aging, which is needed to understand really how can we use this material under these severe conditions, and what are the limitations, and how can we design really components with these materials. So first of all, we need to understand what is the influence of physical aging which comes from viscoelastic processes or reorganizations of the molecules below the TG that takes place in these composites. We need to understand them, and they are compare them and understand how important they are in relation to the chemical aging that also occur, that in the test we're exposing the material to high temperature, where we can start to have hydrolysis oxidation reactions that can eventually cause chemical bond breaking and mass loss due to outgassing. And this is can then also be accelerated by the creation of cracks into the material. We already saw the consequences of physical and chemical aging on the properties. So what we have done is show some results from a study that we've conducted, where we used this material on the right, this thin ply materials with really low surface density fabrics that create really thin plies. And the idea here is to, we know since previous that thin plies has a tendency to prevent this transverse cracking that could be caused from, for instance, from the thermal stresses. And we wanted to see if by introducing thin plies to prevent these cracks, if we could increase the aging, sort of decrease the aging of the materials. The hypothesis was that with fewer cracks in the material, there will be less pathways for exposure of the material for oxygen. So we tested these materials. These are cross sections of laminates that we tried, and they are in scale. And to the left is the baseline material, and to the right is a thin ply material. So it's indicating here that the thin reinforcement actually creates quite a lot of these thin plies as compared to the coarser, more higher surface weight laminate. But they have rather similar volume fractions. Let's see. me see. Okay, now it's responded. It took a while. So we do thermal oxidative stability test by measuring the weight loss, again at 320 degrees over time. So these are the type of samples we place in the oven and measure then the weight loss over time. And we obtain results like this, where we have the weight loss in percentage of mass loss versus the matrix weight that we have over time. So during the 500 hours, we notice an increase in the weight loss. The yellow one is for a baseline material, meaning the satin weave. The red one is also a baseline, the same but from a different manufacturing, and the green one is the thin ply. What we notice, first of all, we notice an initial loss here as well due to moisture loss in the very early stages of the test, and then the weight loss we start to notice weight loss that increase. There is an accelerating trend. There's quite a big variation between the batches, but small variation within the batches. One thing that we clearly observed is there's no noticeable improvement from the thin plies. And what seemed to be more important, if we go back and look at the red one and the yellow one, they are quite different, but the big difference between the yellow one, the one that we lose quite a lot of weight in, and the red one is indicated here, and we see that the presence of initial voids and cracks in the first one was quite large when we looked at the microscopy images, whereas the baseline of the batch 2 was rather flawless. So this seemed to be one of the very important aspects that and we know that since previous also that these kinds of these defects create paths for oxygen and degradation to occur. So it the thin ply appeared to be better when we first looked at it, but after a bit more closer scrutiny, we found that there are micropores also in this material that could create pathways for oxygen and to accelerate the degradation of these materials. Despite the fact that we didn't see any transverse cracking in these materials, we didn't see any improvement in the degradation from a degradation point of view. So lastly, the last item I would like to bring up with which is areas that we're interested in researching further is, and there's a need at least for this application, is fire resistance, and this is an important aspect, sometimes not really researched that much, in my opinion. It doesn't get the attention it deserves because it's going to be a big problem and big challenge for composites. It is a big challenge. So just to indicate a bit on the materials, this is a graph from a review on flame retardancy of polymer materials, just to indicate a bit on the fire hazard of different polymers and where we can find polyimides. And this is what is pointed out here in this graph is the fire hazard here, and again, for some reason, cost is always on these graphs. But we find epoxy up here with high fire hazard, as well as polyamide nylon, which I will be using as comparison. But the polyimide, in this case, as I said, this is a thermoplastic polyimide, but still to illustrate a bit where the polyimides are in terms of fire behavior. So they have they are very good in fire as well, but still this need to be understood further. And in order to save some, so we can go back, by the way, here. So the first way of looking into the thermostability of composites, is the obvious way is to look at the TGA thermogrammetric analysis, and looking for degradation, mass losses, or when running temperature scans. And what we've done here is to analyze composite samples and resin samples. And these are the typical curves that obtained from TGA measurements at different rates. Is that there is a degradation onset of decomposition at around 450 during these short-term tests, both for the composite and the resin samples, and that it degrades and loses. When we run it up to 1000 degrees, we notice a rather small decrease in weight, comparatively small at least, or 86% during this mass loss. So it's not completely combusted even up towards high temperatures like this. And we have 65% of the resin samples after completion of the neat resin samples. These are done in air. The influence of air versus inert environment in nitrogen is illustrated here, and it could be looked at the black curves primarily. If we look at the black curve, the upper one is for when we do the TGA measurement in air, where there's a lot of oxygen that can interact with the resin. But when we have an inert environment, I think this was, or semi-inert at least, the nitrogen, the weight loss is higher here. I will have to look at that. Should be the opposite here. Could be a different. So that's when doing the cone colorimeter, a way to characterize the fire behavior of composites to run cone colorimeter testing, and that's one of the ways to test the fire behavior of composites. We've done some of that as well. So it involves having a cone heater where a certain heating power is applied on the material, and there's a spark igniter that can ignite the flame. So this is applied on the material that is put here, and a load cell measures the weight loss of the material, and the temperature and pressure is measured in order to determine the energy released. And there's could also be collection of particles in this kind of test. So this is a type of test that we've been doing on our materials. And just to illustrate and give some perspective, also presented here are some typical results from polyamide glass fiber composites that that one can observe, that one for traditional polymers. So from these experiments, you usually get heat release rate, which is a heat that is generated by the reacting polymer. You start out with a time which is in this sort of induction time before, when nothing happens, and then the polymer and or sample ignites, and there's a fire, and the heat is generated. And in this case, we have a heat flux of 50 kilowatts per square meter. in the lower one, there is a 35 kilowatts per square meter. What can be noticed, this is then for PA6, the neat polymer, and this is with some nanoclay additive that is added to the polymer. But typically, we can notice the ignition time. The time to ignition here is below 100 seconds, is around 60, so sort of 1 minute. And we notice the scale here is 500 seconds. The heat release rates goes up to around 1400 kilowatts per square meter. By adding glass fiber in a glass fiber composite, this is we have the similar time to ignition, around 1 minute, and takes around 1 minute or 10 minutes for it to completely combust, and there is a maximum peak heat release rate of 200 to 300, so it's substantially lower. So this is typical for polyamide composites. If we compare this with the samples that we have produced for our composites, the polyimide with a T650 carbon fibers, we notice, again, this is the same curve, but I wanted to show the first one just to give a bit of a perspective. The heat flux is 50 kilowatts per square meter. During the first 10 minutes, there is no heat release. There is no ignition during the test, and there's no measurable heat released during, but it delaminated the composite. At increasing the heat flux to 70 kilowatts per square meter, we still, it took around 4 minutes for something to happen, and then it happens. There is some weakly burning flame after ignition that takes place, but it's compared to the heat release rates that we observe for polyamide, this is very, very, very low, and it takes more, and it keeps on burning at a very small rate or low rate until over 13 minutes. So it takes a long time. So if we compare this, some of the key important aspect here is for the fire testing is time to ignition and the peak heat release rate. So we compare the T650 MHTR, which is the composite that we're developing. We see that for 75 kilowatts per square meter, if we increase it even further, I don't have the curves, we have a time to ignition that is 160 seconds, and the peak heat release rate is 65. And comparing it to carbon fiber and RTM6 epoxy, we notice quite a big difference here, that it's substantially better than these epoxies. So with that, I hope I'm planning to conclude my talk now and just give a summary of what in my opinion, I've been trying to convey the message here. So a reminder of what we've been talking about. I hope you agree that we started out by looking at a bit in general about the composites in aircrafts and how the challenges, which is sometimes quite extreme challenges of aircrafts, are really good drivers for composite research and composite development. And not only the aircraft structure, but also the aero-engines are areas where the composites are largely used. And there are some areas where traditional composite can be used, and areas where we need to look into really high performance composites in order to expand the use of these lightweight materials. That we've been using this newly developed polyimide resin type, the thermosetting polyimide with quite extreme thermal properties. How we looked into developing the processing techniques that is required in order to be able to find a good processing window, which is sort of solid materials engineering work. Again, a lot of practical issues that we don't have time to go into here, but a lot of practical issues needed to be solved in order for it to work. Just finding, for example, sealings that works at this 320 degrees is certainly not trivial. So there's a lot of tricks that had to be developed over the period that we've been working. In general, how were the properties developed, that the properties are good, but there are also knockdowns because of aging and temperatures. A bit on how residual stresses are really important in all composite processing, but particularly important for these materials where we process them at such a high temperature. And also about the aging that we conducted. Thermo-oxidative stability is really a key issue that we are keen to understand and develop understanding on how the mechanism for degradation of these materials at high temperature. And lastly, a bit on the fire behavior. Yeah, some acknowledgement. I think it's worth noticing that the colleagues at RISE Comp and the colleagues at LTU is really appreciated. A few persons who are not known to you, but really appreciated by me and the colleagues is Magnus Edin and Spiros Tsampas, who were largely involved in the initial work, and some of the industries and university partners that we've been working with. A few of them mentioned here, and the funding agencies, of course. So with that, I'd like to close. Okay.
Thanks a lot, Patrik. I really enjoyed myself here in your talk. Some familiar things to me and RTM and everything, but yeah, brilliant talk. Thank you. I do have some questions. We have around 10 minutes for questions. So can I start?
Yeah. Yes, please.
Fire away. Okay, I can fire away. Okay, I'm gonna start with the first one here. It's related to one of your earlier slides. It's about bio-based composites, matrix or fiber. Do you consider a tendency to develop aircraft parts with these bio-based composites? And what component could be replaced by these bio-based composite materials?
Yeah, I think the most if we look at replacement and using bio-based materials, it's most likely not the structural part, but for instance, interior parts, floors, semi-structural parts, floors, chairs would be the immediate thing to look into. If you just consider the bio-based fibers, for instance, in bio. But
in that case, the fire problem, how do you see that? I mean, would increase, right? The fire tendency of the material, right?
Could be, but not necessarily. I think need to be also the matrix material is largely governing the. For instance, bio-based fibers could potentially be used with some resin with a high phenol content that is highly charring material, and that could be
encapsulating the fibers, right?
Theoretically, as well as good as a carbon fiber, I think.
Okay, good. There's another one here. Do you see a possibility to consider type 4? That's a polymeric liner instead of metallic-based liner composite pressure vessels for hydrogen storage, next generation aircrafts?
Yes, if we solve the, yes, I think so. That's clearly a possibility. A lot of the, at least in the visions for the hydrogen storage is that a majority of the, it will be in the liquid phase. So diffusion will not be as as important.
Okay. If it's liquid, right, instead of gas. Okay.
Yeah, but at some stage, at some area in the process, when transforming it from the vessel to the engine, it need to go to a gas phase, and of course that in that case, then it will be again very challenging. But hydrogen is I mean that's an interesting research area and something that needs attention. Hydrogen is a very small molecule.
Okay.
And it diffuses easily.
Okay. I have one question here. I think it's the question is, how about erosion and wear properties? I think it's concerning the aero-engines and applications.
Yes, the erosion is probably an issue. I mean, for the fan blades, there is a metal protection on the leading edge to protect the part from erosion, and that is also, to my understanding, I think also considered for, or it is considered for the guide vanes as a erosion protection. So it will be an issue for the composite part. So, and also for the high temperature part, wherever it's exposed to. In practice, to my understanding and my knowledge, it's currently sold by the metallic cover on the leading edges of the component.
Okay, I think those are the 4 questions of Mentimeter. Then now I got two questions of my own. We can finish the time here. The first one is about, I noticed that we had some viscosity values there around 600 millipascal second there. Do you consider that the limit of viscosity allowed for RTM of this aero engine or just aeronautical parts in general? 600 megapascal second? Millipascal, sorry. 600 millipascal second.
We had to decide on a value, and we took that. It is possible to do the experience that we had at CComp and the sort of the infusion test is that, well, it can be, we can do it with higher viscosities as well, but it's not good. It's not ideal. Ideally, the lower the better, and ideally would like to go to something like 150, 200 is a good viscosity to work with, but below 600, we took a number.
Okay. All right. Okay. Another thing is that, I think you mentioned also the fiber volume fraction around 58%. I saw you in one of the slides there. Is this maximum value for fiber content or for RTM parts in general? I mean, or you can go even higher than that?
No, we could go higher than that for some. It depends to a large extent on the preform, of course, and how we orient the fibers in the preform. So if you have unidirectional fibers all in one direction, then we can clearly have a higher compaction of that and reach higher volume fraction. But again, it's always a compromise between different things. Sort of 58% is something we feel comfortable with. The permeability is good. Permeability is good, acceptable. We can do good infusion of the resin, and we also good properties and repeatable.
Okay, that also applies to those thin fabrics that you showed there. Those almost non-crimp fabrics there.
Non-crimp fabric. This applies to largely to the satin weave fabric.
Okay. And that
the thin ply composite, thin ply is a bit more challenging when it comes to processing, because it is very dense and it's very easily compacted. Sometimes it's not so easy to. achieve low volume fractions, because then if you have too low volume fraction, then when you fill the mold, then you displace the fibers, because it's not sufficiently compacted to be to stay there in place. And if you compact it really too much, then it becomes very difficult to impregnate, and so it has a challenging processing window, this kind of materials.
Okay. Oh well, I'm happy with the answers and everything. I need to pass it on to André now, but before that, I really want to thank you again, Patrik, for having accepted straight away our invitation. And I know it's late now in Sweden. It's what is it, 9:30, almost 9:30 p.m. So it's late there now. So thank you for accepting this time also. This time of the day is not very common to present something at this time. So thank you again for accepting this, and thanks a lot for such a brilliant talk, Patrik. Thank you. And André is on you now, please.
Okay.
Thank you.
Thank you, Professor Patrik, for this very nice talk. Thank you again.
Thank you.
Obrigado, pessoal, pela presença nesse terceiro seminário. Lembrando que a apresentação foi toda gravada e a gente vai disponibilizar ela para vocês lá no canal do YouTube da ABPOL, tá? E aproveitando o momento, eu já convido vocês também para participarem do nosso quarto seminário no dia 28 de outubro, tá? Que é com a doutora Cristina Scheffler, do IPF de Dresden, da Alemanha, tá? Na segunda-feira a gente começa a divulgar o evento e abrir as inscrições. Até lá, fiquem bem, uma boa semana, um bom resto de semana, um abraço a todos, tchau, tchau.